This section 7.2, we again continuing doing the um, um, let me see, measuring a quality of a survey. For this one is also a definition describing to describe the quality of the survey. And again, for this is I hope maybe later they will have some more actual example talking about describing the quality of this by computing some we call standard error um, after the sample distributions later. So right here, in order to, before we're doing that, we're gonna using, we call the term accuracy and precisions to measure a quality of a survey. Um, in English, you know, these two words, accuracy, right? Accurate, exact, precisions, it's like precise, stuff like that. It's kind of similar definitions, kind of a bit. You know better than me, right? And the second things is we are learning about describing important features of the sampling distribution. Sampling distributions, like we are saying, we just talked about um, a simple random sampling. It's kind of the same thing. Sampling distribution, we talk more set of sampling, more set of the sample, um, make it up to form a distributions. And here you see the another terms we call standard error. This standard error is it's look like standard deviations. It's kind of that, but it actually is not exactly the same. It's kind of the family. It's a kind of same similar meanings, but it's not exactly the same because they are having different formula. You have learned standard deviation from previous chapters. You are computing by using the formula square root of divided by, it's kind of a bit long, um, square root of x minus x bar, everything squared divided by n minus 1, and everything square root of that. Or I taught you another method like taking the absolute value from each given data from and then subtract the mean, right? And then we adding all of those divided by n minus 1. You take square root of that. So we are having different way. Actually, stat people, they create many formulas, but the two famous formula that I just mentioned earlier is you can apply to find standard deviations. But for this standard error, you're not going to use that formula anymore. But this standard error depend on the question given. Then you will apply the correct formula to compute the standard error. The standard error is like a small error that possible that's make you got the like the wrong measurement, the wrong estimations. But this standard error all the time will be very small value, and again, it's helping us to kind of estimating it roughly. And again, you will see more about this formula later in the next, hopefully the following slides. So here is the evaluating the surveys. Statisticians evaluate a method used for a survey, so not the outcome of a single survey. And so here's the way that they are evaluating the survey. They are using, we call the term accuracy and precision to decide. So here they give us the example. First, if a group of researchers were to survey 1,000 randomly selected people, so this 1,000 is look like a sample size, right? A sample. And we would expect the result to vary from a sample to sample. So here I said they having many groups. So let me describe it for you. So for example, the first sample, they draw out this much. They draw out this 1,000 people, okay, and they do a survey. And again, they draw another 1,000 people, and they do a survey, they recorded the data, and out of this sample, they build up, become the distributions. Okay, so many sample combined form a distributions. So, and again, excuse me. So in here, don't think too much. I hope that you can visualize kind of easy picture. But here is what it say. We would expect the result to vary. So all each usually when they take the survey for each 1,000. So let me say this is 1,000. So they count one at a time. They count one at a time. Okay, they not like add up the whole thing and make become like 4,000, for example. No, they're not doing like that. They count the result from each 1,000. They count from each 1,000. They collecting 1,000 and they asking them the question and collect. They record the solution down, and each of this, they might be the same probability. They might not the same. Okay, so every single time that they do collecting, they selecting about this 1,000, they got different answers, right? Or maybe sometimes it's the same. And because they said, because we would want to know how the group did as the whole. It's like they estimating, they just keep collecting like this, so they estimating so they can draw out like kind of more accurate to the two populations, to the two value. And then we evaluate the estimation method. See, all the time stat they estimating. They just estimating by using the formula, by using the data given, by collecting, they recording, by graphing, stuff like that. So statistics, again, I would like to clarify, it's all the time 100 correctly. They just, even though we compute, we got a number, but that number really just the estimations. It's not real. It's not true. Okay, so let me see if I have example later so that I can explain to you more. Okay, I'm sorry, this color. Okay, erase this. Oh, I don't know why it's like have this line. Oh, maybe this color. Okay, I gotcha. So next, again. So erasers. Okay, class, I'm sorry. Okay, here's select. Okay. The goal is to measuring the quality of the survey. We base on accuracy and precision. An estimations method should be both accurate and precise. So we try to make it as much as accurate, as precise as we could. But again, all the time we just estimate things. Accurate in the stat is here is the method measures what is intended. Okay, intended correctly estimates the population parameters. And precise is if the method is repeated many times. The estimates are very consistent. So precise is mean you will see when you collect, when you do a survey, it's all the time consistent, like this, the same. So, and from there you can estimate the true, estimate the populations. And for accurate, again, it's intended, right? It's will happen. You think it will happen, intended. So, in the example, if the goal is to get the golf ball in the hole, which of these pictures show a method of accurate precise, or both? Okay, so look like the first picture of this a golf ball is kind of close to the hole, right? It's kind of near to the hole, close to the hole. And I think this is really apply for both accurate and precise, for both, right? And for this one, what do you think? It's a bit like you can see the orange is going a bit afar, the white color surrounding it. So this might be accurate to you. What do you think? Just spend a minute. Is it accurate or precise or precisions? It might be like we just get the definitions like what do we have? Accurate is more like it's intended, right? It's like very the estimation is very close, but we have another definition for precise. Precise is mean is repeating many times, repeating, and we got the consistent result. So look like if so, the second picture might be more like precisions and less accuracy, right? The third one is kind of is spread out. It's spread out, and this might be the opposite of the second picture. It will be more accuracy and not precisions. Okay, actually this picture is not, it's just like describing. Okay, it's not like this on the test and what do I do. This is just like the idea for us to looking at the picture and estimate and like guessing. Okay, it's not actual problem at all. Okay, let me see. The first picture shows that accuracy and precision applying into the first picture. The second is show precision but not accuracy. The third picture show accuracy but not precision. Precisions. I'm sorry, my English. Okay. This of my example with simulation one. Simulation one is mean they got the first experiment. Okay, so let's they do the first experiment. What do they have? We have a small population of 8 people, so they have only 8 people. So this time they collecting the sample is only 8. 2 of whom are cat people. 2 are cat people. 2 are cat people. And 6 of whom are dog people. So 6 are dog people, right? So random samples of 4 are taken. So this is like the entire population, we have only 8. So that 8 populations, only 8 only. And they take the sample, which is they would draw out 4. So it's look like, for example, in this group, they just like call out 4 people out of 8. So 4 out of 8, 4 will be the sample, 8 will be the populations. So that's what it means. And the percentage of cat people are noted for each sample. Or could they given us the following: 25% of the population are cat people, and 75 will be dog people. So they look like they given us the probability for each cat people, right, and dog people separately. So they asking, will each sample contain 25% of cat people? So actually, when you draw this, when you draw out, let me see. Let me try to draw out one sample, including 4 people. I might draw the first is cat, the second is cat, the second have to be dog, because two cat only. I drew 2 out already. That's mean none cat. The rest have to be dog. So this would be the cat people they given us is 25%. So this is 25%. So I convert this into decimal number, 0.25, 0.25, and this is 0.75, and this is 0.75, right? So we are having this kind of probability for this four random sample. And will each sample contain 25% cat? Okay, so they asking that question, but okay, I'm pretending. So now the first one I draw dog, the second I draw dog, the third draw dog, the fourth draw dog, because the chance that I can draw dogs is possible because we have 6 dog people in the group, and we just draw out 4. So each of this will be 0.75 for each, 0.75 for each, and so on, right? So, and in order to answer that question, will each sample contain 25% cat people? The answer is no, right? Because I can't draw out this sample right there. So the next question is it, right? Is it possible to get a sample with 0 cat people? Yes, that's what I did. I got dog, 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 dog 4 times. Yeah, it's possible. So that is how that I answer that question. Okay, let me see here. Using a random sample table, three random samples were taken and results are shown below. So here it is. So this is the first sample. This is the first sample. Okay, first sample. This is the second sample. This is the third sample that they drew. I drew out 1, 2. Okay, it's not as same as them, right? Of course. When you draw out a sampling, it can be like this is possible outcomes that when you drew out 4 people out of the 8 people. So the example that we will have for the random sampling will be 1, 2, 3, 4, 5, right? This is 4, 5. You can think of that way, 4 and then 5. 5. This is 4. Those is some. Of course, we can draw more. We can do more than that. Okay, so let's analyze this. What do they want us to do? Let's see. Over here, so the sample proportion p hat. So now they mentioned about p hat changes from sample to sample, but the population sample p remain the same all the time. P will remain the same. For this case, they write notation p hat as a cat people, as they mentioned in example 1 right here. Go back to example 1 right here. They wrote right here all the time. You will see p hat in the question. Here, the percentage of cat people are noted for each sample. So this will be called p hat. So 8% of the cat people inside the set of the sample, we consider that as p hat. Okay, for example, next, for example, that I'm having like this. For example, like this. So for cat people, so this p hat will be 0, right? Because we're talking about cat people, but in this first sample set, we have none. And the second sampling, we have C, only one C represent for 25% cat people. So we have p hat is 25% or 0.25. So this we call p hat changing every single sampling. And I gave you earlier, I got C, C, D, D, right? So this represent for p hat is 50% because we have 2 cat people. So 50% is mean 0.5. Okay, that's what it means. We call that p hat. So this p hat represent for the fraction of the asking element overall the rest of the sampling. Okay, so look like the sample of the sample, right? So p hat is like the sample of the sample. Okay. Let me move on. Go back to this one. We have P all the time because P all the time given is cat people is 25%. So then we will talk only about cat people. We're focusing on cat people only. In the sample, we call P hat is the sample statistics. Okay, the sample statistic. Please remember that. So P hat is the sample statistics. And based on the example that the textbook given to us on page A, it's matching up 0% for cat people, 25% cat people, 25% for cat people. That's what it means. And all the time, the population perimeter will keep the same, which is 25%. That is the fixed value that given. So next here is the distribution. Like I said, distribution is forming when we have many sampling, sampling combined form a distribution. And this is how they graph. They're using the we call a graph. I don't know. So this is look like just a dot, just like graph regularly. There's no name. I don't remember the name, but for sampling distribution graph, people using this graph to describe. Okay, so what? Let's see. This we call the probability distributions, or p hat. You might call this as the describing probability distribution. And again, I said distribution because many sample combined become distribution. Probability because we're talking about probability. We're talking about percentages. That's what it means. Okay. We can use this or this, either one. Either one. Doesn't have to be both. So in this case, so here about the simulations, our estimator is p hat represent for sample of sample is not always the same as our perimeter, not all the time. Sometimes it might be the same, that's what given. Most of the time it's not. The mean of the sampling distribution is about 25%. The same as the value of p. This indicates that the estimator is unbiased. If sometime we can compute the sample and we found that p hat is equal to p, okay, we call this unbiased. Otherwise, it's biased. Actually, it's not really necessary. They don't question you like, is it unbiased or biased? They're not gonna answer. They're not gonna ask you that type of question. But here it's kind of a bit information that you learn. So even though p hat is not always equal to p, the estimate is never more than 25% put away from p. So they said like all the time is around about 25%. In this case, only in this case, okay? Because p is giving us like about 25%. The p hat will be around each p hat. The differences of each p hat is around 25%. The standard error. So the standard error is what I tell you is important, is the way that for us to compute so that we can avoid some error. The standard error is the standard deviations. Okay, it said it looks like the standard deviation, but it's not the standard deviations. It's the standard deviation of the sampling distributions. Okay, so if we're talking about the distribution, we call sampling distribution, is mean many sample combined, stuff like that. So we can call the standard error as a standard deviations. Okay, but again, this standard deviation is not like the standard deviation that you learned before. We have different formula. So it's measure how much an estimator typically varies from sample to sample. Okay. So when the standard error is small, we say the estimator is precise. The SE or the standard deviations is small, it's good, right? Because it's helping us to estimate the actual value easier, more precise. So now this time they're using the larger population instead of 8. Now they're using about what? This time we consider a population is about 1,000 instead of 8 in the first simulations 1. Now this time they want us to consider a population is like about 1,000 people. It's a lot. And again, remember, the more population that you have, the more number that you have, the better of estimations. 8 is very small for us to estimate the actual value, but 1,000 is kind of okay, the average. Some people might using like about 100,000, 10,000, 2,000, stuff like that. But those kind of value is large, so they're going to using a system, a technology to do it. Is we cannot compute by hands. If it's around 8 to 10, we can compute by hands, right? Like easy compute by hands, but it's like this much I cannot compute by hands. So, but we will have the different method for us to help us to compute by hands by using the formula. So this time they draw out instead of compared to simulation 1, we draw out 4, but this time we draw out like about 250. Okay, and this time the cat people again, they still give us like 25% of the population as a p. Okay, we take the random sample of size 10 and find the sample proportion p hat. Okay, so this time again they for those people, 250 divided by 1,000, that's our p hat. So they given us the entire population is 1,000, so our p hat will become the sample, which is 250 divided by 1,000, given you this cancel, that cancel, 25 divided by that become 1,4, right? 1,4 represent for 0.25, and that's equal to 25%. So okay, again, so this case they consider a cat people is like again is 25%, and we are taking random. So for this amount, they will take random like about 10, and find the sample proportion for each for p hat. So side 10 in this case is like sample of sample. Now this time, the last time we draw out only 4, this time we draw out at 10. And in that 10 people, we got 25% are cat, and the rest will be, let me see, of cat people in each example using technology. 1,000, 10,000 sampling we're taking and result also in a graph. Next slide. Let me see the next slide. What the graph do we have? We having this. We have because we draw out 10 this time. The probability is changing. It's not all the time will be like cat 25 and 50 and 75 anymore. So this time, because we are talking about, for example, let me see, I have might be like cat, dog, dog. It's like this, 2, 4, 6, one more. Okay, it's 10 now. So we compute this probability. So that's why the probability that you notice for this bar graph is changing. 20, 0, 20, 40, 60, 80. And again, right here it will be 10%. 10%. This is maybe 30%, and so on. It's changing. It's not as same as, but the more sampling that you will see the bar touching each other, because it's the more data, the better. Okay, let me see. So here is looking at the data. We're still talking about simulation 2. See the center of the distribution is about 25%. The bias of p hat is still 0. Okay, even though a larger population and a sample size were used. The variation of p hat is less compared to the first simulations that you notice. The first simulation is no more than 25%, but this time is like, go back to this. You see that the separate between this is like about 10%, right? 10% is less because it's more data. This estimator is more precise. It's more precise compared to the first simulations, okay? Because it's more data. More precise, even though the population is larger. In general, the precision has nothing to do with the size of the population, but only with the size of the sample. Okay, again, there's a simulation 3. They give us the third example for us to compare. Similarly, using the same population is 1,000, but this time instead of they draw out 10, they draw out 100. Let me see. This time we increase our sample size from 10 to 100. Okay, and they take the number of the sample is about 10,000. It means like they take 10,000 times each 100. Okay, so for example, they take cat, dog, and so on to 100. They take a 10,000 times. Again, this way they have using technology, and they're having the following graph. They're using technology by StatCrunch. We're having this now. You see that the graph touching each other because there's look like there's no more space. Look like the variation we call the standard error very very small now. Okay, so maybe small that we don't even know, don't even count. So here they analyzing the estimation method remains unbiased. The center is still 25%. The population of the proportion look like p will be the same thing still. The shape of the histogram, now this one we call histogram because the bar touch, and the other one they not. Sometimes they call histogram, but mostly they call this become bar graphs. Okay, next, look more symmetric than the one for the sample size 10. The estimator is more precise because it's used a larger sample size. Standard error is smaller than the sample size of 10. So they give us a hint. The standard error is very small. Notation for the standard error will be SE. Now they are giving us summarize for all these 3 simulations. Again, no worry about like, okay, I don't know how to do it. I don't know how to compute that. This is not really the purpose of this chapter. Okay, the purpose of the chapters here, you need to know how to figure it out by using the formula to compute standard error. From there, you will compute we call confidence interval. That's the purpose of the chapter 7. Now it looks like they given us a big picture first for you to see that, okay, that is how they simulate. That's how we are having p hat, stuff like that. So they give you the ideas, okay. And again, you should understand those ideas too as you follow along. A summary of 3 simulations. The first is estimated p hat is unbiased for all sample size. The reason is p hat all the time changing. That's why it's unbiased. So when the estimated p hat is unbiased for all sample size. It means we are having, even though p hat is changing, so p will mostly keeping the same value. P is not changing. That's what it means. So the second is the precision improves as the sample size get larger. So it means we having the larger value that we draw our samples. We get more chance to get close to the true value. Third, the shape of the sampling distribution is more symmetric. The more sample size that we have, we're having the symmetric shape. which is good because we can compute easier by looking at symmetric graph. Because if we got the skew right or skew left, it's not helping us to estimating the true value. So symmetric is the best that we're looking for. It mean the more it mean like they want us to having more sample as possible. Okay. So now next, finding bias and standard error. So this is the point, the key point is here right now starting. The bias of p hat is 0 and the standard error of p hat is compute at this. So in short, they after 3 simulations they want to give us is p hat is 0 is mean is equal to the mean, equal to p. It stay in the middle. We're talking about symmetric distribution over here. That's what it means. And all the time, we're going to use this formula to compute standard error for all of the problem related to we call sampling distributions. Okay, so P here is the probability of proportion, populations. Actually, 1 minus P is our Q, but you don't have to worry about that. You can apply this formula, square root of P times 1 minus P, everything divided by N, using this for now. But later on, we're having different formula depend on different story. So now stick with this one we call standard error of p hat. Then you compute that. So, and they give us the requirement. If the following conditions are met, the first thing is the sample is randomly selected from the population of interest. So this is when you are reading something is similar to the first 3 simulations, then we can consider using this formula. Second, if the sampling is without replacement, okay, they prefer without replacement. The population must be at least 10 times larger than the sample size. So this, we have sometime to do the math. We take the value that they provide, you multiply with 10, okay? You will having the bigger value. I think bigger than 10 will be good. So, okay, this kind of the beginning of the main topic in chapter 7, we call standard error. This is, I would like to jump to the 7.3 so that you can see right away the important about this formula. Right, so look like 2 sections they given us, like many definitions.